Tanks are the most effective weapon on the battleground. They can detect and destroy the enemy with pinpoint accuracy. They can traverse rough terrain at speeds of 30 miles an hour and withstand a direct hit from a rocket-propelled grenade. With their digital command and control capabilities, they can stalk prey day or night. Their combination of firepower, mobility, and armor is unrivaled. Today's tanks are the product of nearly a century of tank evolution, stretching back to the trench warfare in World War I. We examine the technologies that changed this into this and created one of the most powerful tanks in the world. The tank is the ultimate war machine. The power of an artillery gun, the maneuverability of a jeep, and the protection of 2-foot-thick armor. And the ultimate tank is this, the Abrams M1A2. Unstoppable, lethal, and inside, 4 men are safe from almost everything the enemy throws at them. It's computerized, versatile, a digital war machine. The crew is the heart and the brain of the machine. But the tank they control is the best of the best.
If we get a target, I guarantee you within 4 seconds, it's going to be dead. That's a given.
These tanks are made to kill and do their job and bring our boys home. And that's what they do.
The journey from a steel box to a fully loaded, digitally enhanced war-winning machine began almost 100 years ago in the First World War. Tanks were invented by the British to fight among the trenches. German guns had the British pinned down. The British needed a way to break the stalemate. They came up with this. An armor-plated machine that used caterpillar tracks to straddle the enemy's trenches and fire down on them. It lumbered along at just 3 miles an hour, but it spread terror among the German ranks. Warfare would never be the same. Robert Cameron is a historian at the U.S. Army's Armored Branch at Fort Knox, Kentucky.
It's easy to imagine the consternation of the first German machine gunner to see a metal box coming across no man's land toward him. And at some point, that courageous machine gunner would have decided that discretion was the better part of valor, and he would have disappeared.
There was no way to fight back. Machine guns were powerless. The effect was devastating.
Tank panic is one of those things the tank brings to the battlefield, just the fear factor of a large metal box running over you. And you can find this anywhere tanks have been used.
Tanks are successful because they combine the 3 key ingredients any army needs. First, mobility, the means to move in hard and to gain ground fast. Next, protection. A tank can take a hit and still engage the enemy. And firepower, the destructive force to crush the enemy's ability to fight. Improving these 3 elements has provided the impetus behind most leaps forward in tank technology. But they have to be balanced. Too much armor and too big a gun, and the tank will be bulky and dangerously slow. A lighter, faster enemy tank, but with the same firepower, could outmaneuver it and take it out. But put too much emphasis on light armor and mobility, and the tank would be vulnerable to guns from bigger tanks. Get this balance of firepower, mobility, and armor wrong, and on the battlefield, machine and crew face almost certain destruction. Get the balance right, and you have a war winner. One tank that got it right is the Abrams, perhaps the most effective war machine ever made. But behind all the high-tech design and futuristic technologies, three elements make the difference: mobility, armor, and perhaps the most important, firepower. Because at the heart, every tank is just a shell-proof mobile gun. It's an artillery system with the transport built in. The first tanks had either a 7.7mm machine gun or a 57mm small cannon. By World War II, tanks like the Panther had rifled guns which fired 75mm shells. Today's guns are nearly twice as big and much more powerful. Retired tank commander Dave Pride is an expert on the development of the tank's main gun.
The evolution of tanks over the years since they first rolled out in World War I, the guns have gotten bigger. We went through, 75, 90, 105 millimeter. Now we're on the 120 millimeter.
The bigger the gun, the bigger the shell, and the greater the destructive power.
The gun is awesomely lethal, and you don't have to be a soldier in the tank to understand its power. The Abrams main battle tanks can fire in all weather, both day and night, especially on the move.
On the Abrams, the gun alone weighs 2,500 pounds and is 17 feet long. It can fire a shell over 6 miles, as far as any other tank on the battlefield. But the secret of its power is the huge diameter of its barrel. At 120 millimeters, it takes shells that are longer and wider than other guns. Wider and longer shells have a larger propulsive charge and pack more high explosives. This means they travel faster and are more destructive. It's a deadly combination. The 120 millimeter gun fires shells further and hits deeper. But that advantage is not just down to size. In the past, tanks used a rifled barrel to spin the projectile when they fired. Like the rifling inside a conventional gun barrel stabilizes a bullet, it stabilizes the shell and prevents it from tumbling. But that only works on projectiles if they are short in relation to their diameter. Armor-piercing shells are long and thin. Thin, long shells travel faster and concentrate their destructive force into a small impact area. But they can't be stabilized by rifling. The 120 millimeter gun has a smooth bore barrel which doesn't stabilize the shells at all. Instead, they stabilize themselves. The rounds are dart-shaped with fins that stabilize the shell in flight. This gives the tank an added advantage. A smooth-bore gun fires shells faster than a rifled barrel, increasing range and destructive power. The 120 millimeter gun has two main types of ammunition: the high-explosive anti-tank or heat round, and the armor-piercing, thin-stabilized, discarding sabot tracer, known as the sabot.
We have the sabot, which is a pure armor-defeating weapon. It's made for killing tanks and tank-like targets. The heat round is a high-explosive weapon. We use it for lighter-skinned vehicles. We shoot personnel carriers and stuff like that.
Both round types pack a mighty punch, but they destroy their targets in different ways. The sabot round works like an arrow. The crucial part is the penetrator, a narrow metal dart within a larger jacket or sabot. The sabot is there to fill the 120 millimeter barrel and to keep the dart dead center. It also gives a greater area for the propulsive charge to push against. The moment it clears the barrel, the sabot falls away. Without the bulk of the sabot, the dart's air resistance is tiny. It flies toward its target at 3,500 miles per hour. When it hits, the dart's narrow shape focuses the full force of the round into an area smaller than a quarter, blasting straight through the enemy's armor. Heat rounds use an explosive charge to penetrate armor. At its nose, the charge has a sensor. When the sensor hits the target, it ignites the explosives inside the shell. This heats the copper lining of the charge to thousands of degrees Fahrenheit. The molten copper is compressed into a narrow jet that blasts through the armor at up to 25 times the speed of sound. The intense temperatures liquefy the metal in the armor, sending lethal shards of hot metal throughout the tank, hitting the crew. With weapons this powerful, accuracy is paramount in all conditions. Weather, particularly temperature, can drastically affect the performance of a gun on the battlefield. Dave Mann and his team at National Technical Systems at Camden, Arkansas, study how shells perform in different temperatures. Temperature can disturb the trajectory of a shell in flight. Today, they are testing rounds destined for Iraq, where temperatures can reach 130 degrees.
We're in Iraq now, where temperatures get up to 120, 140 degrees, even higher in those tanks, and they have to know that those rounds are going to hit on target at those temperatures.
To mimic these conditions, Mann and his team placed the shells in an oven overnight to heat them to 140 degrees before testing. A series of sensors will monitor wind speed, barometric pressure, temperature, and the shell's trajectory in flight. The speed of burn of the propulsive charge is critical.
Green light. Range clear. All right, here we go.
Burn too fast, and the shell's flight becomes erratic.
5, 4, 3, 2, 1.
The shell leaves the barrel at over 3,000 miles per hour. It travels the 8,000 feet in less than 2 seconds. The test is a success. The heated round maintained a normal trajectory and hit the target. Such tests help crews on the front line to trust their technology, freeing them to make critical decisions.
When you're out on the battlefield, we know that those weapons have to work correctly. We know that lives depend on what we do.
In Iraq in 1991, almost 2,000 U.S. tanks provided the firepower for a decisive victory. In just 100 hours, the world's fourth largest armored force was reduced to scrap metal. The firepower of modern tanks is second to none. But even so, life on the front line is extremely dangerous. Tanks can seek and destroy almost any target, but they aren't the only big guns on the battlefield. The engineer's next challenge is to keep them looking like this, instead of this. On the battlefield, packing the biggest gun doesn't guarantee victory, unless you also have the armor to protect the crew and weapons. The first tanks were made of simple steel plate. Tanks now use the latest armor technology to create the ultimate war machine. The Abrams tank is manufactured in sections at the General Dynamics plant in Lima, Ohio. It's built with a modular design. Technicians can install new features without having to rebuild the whole tank. Manager at the Lima facility is Keith Dieters.
The designers of this thing built one heck of a vehicle. Just can't stress enough how this vehicle was designed and intended for use, not only for now, but all the way up to 2035.
The main challenge building a tank is that you only get one chance to get it right.
You don't always build a product that somebody's going to shoot at with intention of killing you in it. And with that thought, it's very important that you've done it correctly. We're building a product that, if it doesn't go right, it could cost you your life.
The armor on the tank has to provide the protection for the vehicle and its crew. But if it carries too much armor, it can't move fast enough. The challenge is to gain maximum protection with minimum weight. For modern tanks, the armor is cut from steel plates and classified composite material formed from layers of ceramic and metal. In places, protection is up to 2 feet thick. But very thick armor is not the only way to protect against an attack. Designers can increase the effective thickness of the armor by sloping it. This technique of sloping armor dates back to the 1930s. Soviet tank designers started to slope the armor on several tanks, most famously the T-34. The 45mm front armor plate on the hull was sloped back at an angle of 60 degrees. This had an immediate impact in the field. German tank crews were horrified to find that shots fired at T-34s were often ineffective, and some would simply bounce off. Sloping armor repels enemy shells because angled armor plate increases the chance of deflection and increases the effective thickness of the armor. Most contemporary tanks have sloping armor on their more vulnerable turrets, just like the T-34 70 years ago. That increases what's called the line of sight thickness, the amount of armor a projectile would have to penetrate along the line it's traveling. Compared to non-angled armor, sloping armor increases the effective thickness of the armor plate, so when a shell hits, it reacts like it's hitting a much thicker sheet of metal. Sloping armor increases protection without increasing the weight. The tank retains its mobility while maximizing its protection. But even with sloping armor, most tanks are seriously heavy machines. Fully loaded, the Abrams weighs 70 tons. Nearly 3/4 of that weight is armor, around 50 tons. That's much more than the weight of a T-34 tank. Even the welding that holds it together weighs over half a ton. Armor has come a long way from the half-inch boilerplate that covered the first tanks. It's had to. Today's tank armor protects against more than just shells. The seals on the Abrams are engineered to make the cockpit completely airtight when combined with the air pressure regulator. It's not just immune to shells, but to chemical and biological attack. But the rules of war change constantly, and that means engineers must constantly reconsider their design. Recently, they discovered a new problem in the street battles of Iraq, a new battle arena with new rules of engagement. To keep weight down, the Abrams armor is thickest where a threat is most likely, on the front and on the turret. The sides have less armor, and the rear and roof are the least protected. In conventional warfare, that's not a problem. But in the close-up street battles of Iraq, insurgents with homemade bombs and rocket-propelled grenades have targeted vulnerable areas like the engine compartment. Scientists have developed new technologies to protect tanks and their crews in urban areas. When the fight turns to the streets, the rules change, and so does tank design. Engineers have developed a technology that fights fire with fire. To stop an enemy explosive shell from penetrating the tank and killing the crew, they have created their own explosion to drive the destructive energy of incoming rounds away from the tank. Tanks are the steel fist of warfare, capable of destroying their enemy without mercy, day or night. But warfare has changed. Today, tanks must perform as well in cities as they would on a more conventional battlefield. And that leaves their thinly armored sides exposed. But adding thicker armor won't work. It adds too much weight. Engineers had to come up with a different solution. It's called reactive armor, a system that prevents shells penetrating the tank by literally blowing them away. It consists of a series of explosive flyer plates that cover vulnerable parts of the tank. The tank is literally covered in high explosive. The flyer plates look like small boxes. They contain an explosive that is detonated only when hit by a rocket or missile. On impact, the explosive ignites and pushes the force of the incoming projectile outward. Socorro, New Mexico, 10 a.m. An explosive expert Van Romero and his team are about to conduct a demonstration to show the protective power of this type of armor. As Vice President of New Mexico Tech, one of America's leading research centers for explosive science, Romero has been at the forefront of explosive technology for over 25 years. He's demonstrating how reactive armor repels armor-piercing shells.
What we're going to demonstrate today is the basic principle behind a flyer plate. And this basic flyer plate technology is used in all reactive armor.
In our first demonstration, Romero will fire a shell at standard armor with no reactive flyer plate. The team use a shaped explosive warhead, like those used in a rocket-propelled grenade, or RPG. The explosion is focused on the copper lining, creating a jet of molten copper that punches through armor.
We're going to have about 10 inches of armor, fire the warhead right next to that armor, and cut a jet through 10 inches of steel.
By 5, 4, 3, 2, 1.
To the naked eye, it's all over in a flash. The only way to see what's happening is on high-speed cameras. At an incredible 10,000 pictures a second, we can see that the copper jet slices through the 10 inches of steel like a knife through butter. The superheated jet of burning copper instantly liquefies the metal in the armor as it punches in. It cuts through the armor at hypersonic speeds, up to 25 times the speed of sound. In a combat situation, this could have been lethal.
And then they exit.
The inner layers of armor would have shattered, sending shards of hot metal through the interior, striking the crew and probably igniting the fuel and ammo stores. Reactive armor is different. In the second demonstration, Van Romero sandwiches sheets of flexible explosive between a 1-inch block of steel and the armor, creating the reactive flyer plate.
As the warhead starts to cut through the outer metal and into the high-energy explosives, the explosives will ignite and push the flyer plate into the incoming jet. That will defeat the incoming round and protect the tank.
The idea is based on simple physics. The shock and the heat of the jet from the RPG coming in presses down on the high explosive and detonates it. This shoots the flyer plate out, and that pushes against the armor that's behind it. The combined pressure forces the explosive charge away from the tank.
Simple technology, but it works. And all reactive armor is kind of based on that simple principle.
3, 2, 1.
What's that?
Went boom.
It did, yeah.
Once the metal has cooled, Romero examines the armor. The jet has cut a small hole in one side, but has not pierced the whole way through. The exploding armor is triggered by the initial impact of the shell. It blasts outward, neutralizing the effect of the impact before it ever reaches the inner layers of armor plate. High-speed footage reveals the astonishing difference between the armor that hasn't been protected and the one that has.
This jet is what gets into the turret of the tank and causes havoc with the crew and everything inside the tank. What we've managed to do with the explosive armor is eliminate that jet from getting inside. You see here, there's absolutely no jet. Well, you can see the shape charge perfect. Big difference.
It's an astonishing technology, a simple reactive blast, but it's enough to completely block a superheated jet of copper traveling at 25 times the speed of sound.
All of the energy is being expended on this side of the armor, as opposed to the energy going through the armor and escaping into the turret of the tank. And so it worked perfect.
An RPG hit is severe, but without reactive armor, the crew would almost certainly be dead.
Even with this protection, it still is a pretty rocky ride inside that turret. It's no picnic when you get hit like that. You know it, but lives will be saved.
The real brilliance of reactive armor is that it saves lives and machines without adding very much weight. To do the same job with conventional armor would require 10 times the amount. But because reactive armor weighs around a ton, the tank stays light, fast, and maneuverable. Out in Iraq, reactive armor has already saved lives.
We did get hit with a couple of homemade RPG grenade-type devices that it was more of a shock therapy for us, but it bounced off and we kept on rolling.
Reactive armor gives tank crews the edge in battle and the confidence they need to confront the enemy head-on.
You can sit there and you can feel a round bounce off of you, an RPG round. This item that is designed to kill you is ineffective. It gives you huge amounts of confidence that you can continue to step forward in battle. And now you can go into areas that you did not before.
But even the most heavily armored tanks can be vulnerable to a fast-moving and well-armed enemy. The ability to get anywhere and get there fast is key. Without mobility, a tank isn't a war machine, it's just a target. Ever since its debut on the scarred terrain of World War I, the tank has played a decisive role in land warfare. Throughout its evolution, soldiers and scientists have used all their ingenuity to design the best tank. Bigger guns, devastating ammo, impenetrable armor. But without one extra ingredient, none of this would be enough. The tank's power comes from its ability to go anywhere. Without mobility, a tank is just an overweight armor-plated gun. Even back in World War II, mobility was the decisive factor. In 1939, Hitler launched the Blitzkrieg, a sudden, devastating armored strike. Panzer tanks smashed through Polish lines, encircling and destroying their opponents. But the Panzer's dominance lasted just 2 years. As they pushed east, eventually they confronted the Russian T-34.
In the T-34, at that time, the Russians had a vehicle for which the Germans had no equal.
The Russian T-34 could outmaneuver the German tanks. The key was a suspension system that was actually an American design. It turned the original lumbering Caterpillar track tanks into a high-speed, all-terrain attack weapon. Caterpillar tracks are made up of a series of connecting metal plates looped over wheels. The first tanks used them in 1915 to traverse rough ground that would have defeated the wheel. But they had a rudimentary suspension system that limited the tank's speed to just 3 miles per hour. Then in 1928, a brilliant designer called Walter Christie smashed that limit to pieces. He built a lightweight tracked machine that moved at astonishing speed. The prototype had a low-slung chassis and, for the first time in a tank, an independent suspension system for each wheel. In the past, tanks used a simple leaf spring suspension system. This type of suspension consists of several layers of metal called leaves bound together to act as a single unit. Many trucks and heavy vehicles still use this design today. Christie's system was different. The separate suspension units allowed each wheel far greater freedom to move up and down. It gave his tanks a huge advantage cross-country. The U.S. Army didn't adopt his system. Christie was too difficult to work with.
The problem is that he was kind of the archetypical eccentric inventor. He had difficulty working as part of a team.
Instead, Russia bought it and incorporated it into their new tank, the T-34.
What the Russians did is they took the Christie suspension, they analyzed it, they studied it, and they took what the best features of it and they incorporated this into the T-34.
The Christie-derived suspension permitted high speeds in rough terrain. A tank's cross-country performance is crucially dependent on suspension. A poor suspension system shakes the crew so violently that even simple operations become difficult. That limits their speed and makes firing on the move next to impossible. The T-34 changed that. It could travel cross-country at 25 miles per hour. The German Panzers had a top speed of just 12.5 on rough terrain. The T-34 also had wider tracks. Panzer tracks were 15 inches. The T-34's 22. It could cross mud and snow faster and more comfortably than the German tanks. Christie's innovations are still seen in today's state-of-the-art fighting vehicles, which feature an independent suspension system like the one first conceived in 1928. The tank's engine rotates steel sprockets which move the tracks, carrying the tank forward over all types of terrain. Each track is 50 feet long, made up of 79 segments with replaceable rubber blocks. The tank's dual 7 wheels are attached to a spring suspension system, each allowing 15 inches of vertical movement. The tracks spread the weight of the tank over a large surface area to prevent it from getting bogged down. The Abrams exerts a pressure of only 15.4 pounds per square inch. That's half the pressure of an average woman when she walks. To move something this big takes power. Other tanks use diesel engines, but at 70 tons, a regular engine would struggle to drive the Abrams up to its incredible top speed of 41 miles per hour. So it doesn't have a regular engine. It uses jet power. The tank's turbine engine produces 1,500 horsepower. That's nearly 7 times more power than your average SUV. The engine produces its own pressurized gas by burning jet fuel. The heat that comes from the burning fuel expands air, and the high-speed rush of this hot air spins the turbine. The tank can accelerate from 0 to 20 in 7 seconds and generate a cruising speed of 30 miles per hour. It's a gas guzzler. It gets less than a mile per gallon, but the advantages outweigh that. The jet engine is not only more reliable than a diesel, it's quieter. So quiet that troops have nicknamed the Abrams Whispering Death. It's the most mobile and maneuverable tank ever designed. Colonel Scott Flynn gets to test it.
It moves extremely fast. You'll get speeds 40, 50 miles an hour in the tank, and during that time you have the full stabilization capability to shoot on the move.
Flynn tests the suspension on the bump track. Tanks with limited suspension subject their crews to massive shaking, making accurate firing on the move impossible. Finally, the slope test. The tank can traverse slopes up to 60 degrees and hold steady. It's also a speedster, with a top speed of 41 miles an hour, nearly twice as fast as the Russian T-34.
The power that is inherent in the tank, it definitely plays on our enemies. When they see that tank coming up, it's an attention getter.
Amazingly, this speed doesn't prevent it from hitting targets on the move. It can spin its turret, all 26 tons of it, 360 degrees in just 7 seconds, without having to slow down. It can lock on a target and fire with total accuracy while still traveling at high speed.
It's a very fast tank. It's an offensive tank. The ability for us to move very fast and engage moving targets sets it apart.
Tanks and their crews have proved themselves time and time again, and they are still evolving. Modern warfare is not just about weapons and mobility. It's about information. It's now entering the digital age, where wars are won not just by who's got the biggest weapons, but by who digitally controls the battlefield. Since tanks first rolled out onto the fields of Flanders, they have evolved into masters of warfare. Now they have entered the information age. The Abrams is the most advanced digital tank ever.
It's the best built tank in the world. Technology-wise, we don't know who could beat it. It's, the soldiers refer to it sometimes as a 65-ton PC.
The latest Abrams uses a system enhancement program that controls navigation, sensing, and targeting. Its global positioning software can pinpoint its location anywhere on the planet to within 3 feet. A key component of the package is its range of detection systems, among them night vision. The tank can operate just as effectively in the black of night as in broad daylight. Night vision systems are not new. Early American night vision systems were used extensively during the Vietnam War. They worked by amplifying and intensifying what little light there was, even starlight. But the Abrams is different. It uses a thermal imaging system that needs no light at all. Thermal or infrared energy is not visible to the human eye. In fact, we sense it as heat. Everything with a temperature above absolute zero emits heat, even when there's no visible light at all. The hotter the object, the brighter it glows.
You can see how the different parts of that man's body is highlighted for the heat. And as we continue to go across the field of view that we have, we check out for other types of heat sources, other personnel.
The tank's computer takes the heat image of what's outside the tank and converts it into a regular image.
Out in the testing area where we used to test these at night, you could actually see if a dog would walk across the test area. You could tell if he had a thick coat or a thin coat. 2,000 meters, you could tell where he walked, if he laid down for a little bit and continued to walk.
The enemy can't hide. The gunner sees the warm target standing out from the cool background. This technically enhanced system enables the tank to penetrate darkness and dust with a clear 120-degree view.
Because we got a saying, we own the night, and we actually do. It could be 2 o'clock in the morning, pitch black, and you couldn't see your hand in front of your face, and I could see you probably 2 miles away.
A state-of-the-art infrared camera allows the commander and gunner to stalk and prioritize enemy targets. The commander also has a second camera, so while the gunner is firing, the commander can be searching for the next target. When he finds one, a simple button push automatically brings the tank's gun in line with it. As the gunner deals with that target, the commander hunts for the next, all in a matter of seconds.
As soon as one of you identify a target, if it's the tank commander, he hits a button, the gun goes right to it. While the gunner's getting the range to that target, he's ready to shoot and kill that guy. The commander's already off that target looking for the next one. So depending on how fast your loader is, hopefully somewhere around about 4 seconds, you're putting steel on target about every 4 seconds.
The tank has a digital fire control computer that is connected to sensors on the gun and turret. These automatically measure the muzzle alignment to maintain a high level of accuracy. Extreme heat can change the alignment of the gun barrel and sights. The tank has a computerized muzzle reference system, which monitors changing temperatures and barrel position. It helps the gunner to realign the barrel and sights and put metal on metal. The combination of crew and computing helps them hit 6 targets a minute from over 2 miles away. But like any modern computing system, each individual tank has limited information and processing power. Making the best decisions requires information from the whole battle arena, so the computers on the Abrams network. It can talk digitally to other tanks alongside ground and air forces through a central command system. This networking has revolutionized tank warfare. Commanders can coordinate attacks from the air and the ground, and so control the battlefield. The tank has come a long way. What started off as an unwieldy steel box in 1916 has evolved into a hyper-sophisticated weapons system. Almost invulnerable, deadly accurate, and supremely powerful. But warfare changes constantly. The tank must continue to evolve. There are new threats, new anti-armor weapons, smart bombs, artillery drones, even electromagnetic bombs, which can cripple onboard computers. Military historian Robert Cameron is in little doubt that the tank's role in warfare is assured.
The tank has always been subjected to criticism that it is too heavy, too costly, and that there are cheaper, more efficient systems out there that can replace it. And yet today, tanks, those dinosaurs of the past, not only are functioning very effectively, but they are in demand.
The tank's ability to adapt is its key strength. It can fight virtually anywhere.
In Operation Iraqi Freedom, one of the things that's interesting is that tanks have been used to spearhead attacks into towns and cities precisely because the onboard sensors, the firepower, and the survivability. It's infinitely greater than a rifleman by himself walking down the street.
I can't imagine a scenario where there will not be a requirement for a mounted platform that offers survivability, speed, shock, and firepower.
The immediate objective for tank designers is the same as it has always been: to ensure the survival of the men who crew these vehicles and give them the technology and firepower to win the battle at hand.
I think that the tank will be around for a long time. We've seen evolutions in lethality, larger guns. We've looked at directed energy, lasers, other things like that. But it's the ability to provide that shock effect and firepower, break the enemy's will to fight. And tanks do that very, very well.
Firepower, mobility, protection. The tank has all three.
As a soldier, it gives you a lot more confidence. You've got this additional armor around you. You've got this greater capability to take damage and dish it out, and now you can go into areas that you did not before.
From the fields of Flanders to the streets of Fallujah, the tank is triumphant.